And we are live. Hi, I'm Frank.
Hi, I'm Jackie, the teaching assistant.
And we're here for Astronomy 111X on our second Google Hangout. So we've got a little agenda planned. Jackie's going to talk about some astronomy and movies. And then I'll do a quick tour of the sun in a rocket spaceship. And then in between and sort of afterward, depending on time, we'll cover some of the questions that were asked in our discussion forum. You can also ask questions in the live as we go here. There should be a chat box, and you can write your questions in on the chat box. So with that, I'm going to mute, and I'm going to let Jackie take it away.
Okay, so I'm actually here with my lovely assistant, Chester. Chester! So there may be some racket as I'm giving this presentation, and I'll do my best to curb that, but I actually live in a zoo. So I'm going to talk about bad astronomy in good science fiction movies. And the three movies that I've chosen for discussion are Interstellar, Gravity, and The Martian. And I actually just finished The Martian, the book and the movie, in the last month or so. And I read the book on an airplane, and then the movie came on while we were flying across the Atlantic Ocean. So that was cool. So good science fiction movies in the sense that they are trying very hard in all three cases to actually base the motivation for the story on actual scientific premises that have true astronomical provenance. Bad astronomy in the sense that, well, they were Hollywood, so they took a few shortcuts. And some of the science doesn't actually hold up in detail. So I'm going to start with Gravity because I probably had the highest hopes for it. Gravity is based off of a phenomenon called Kessler syndrome. And there will be a spoiler section in this discussion. So I'm gonna have a little hand wavy gesture for like, you should stop listening when we get to the spoilers, and then I'll do another hand wavy gesture so you can start listening again when they're over. But to begin with, the premise of Gravity is that the space shuttle, which of course there's no space shuttles anymore because we canceled the space shuttle program, but in a future in which we do have space shuttles, is up there repairing the Hubble Space Telescope, installing a new camera in it, when a catastrophic collision occurs between low Earth orbit satellites. Two satellites collide, and the debris from the first collision takes out a couple more satellites, and the debris from subsequent collisions continues to create a chain reaction, which creates a giant debris cloud, which keeps hitting the space shuttle, the Hubble Space Telescope, the International Space Station. Everything that's in a low Earth orbit eventually gets taken out by this debris cloud, this growing debris cloud, which comes around every 90 minutes. And that part of the story is completely accurate. First of all, how do I do screen share? I always have to figure this out every semester. Do desktop, start screen share. So the concept of, hey, Frank, can you see the Kessler syndrome page?
Yes, I can.
Okay, cool. So Kessler syndrome is the phenomenon that the movie is based off of, and it's a real thing. And this actually relates to a question that one of the students, Olga, had in the thread about topics for the Google Hangout. So Kessler syndrome was proposed as early as 1978 by a NASA scientist who realized that we had put so many things up there that the chances of collision had grown exponentially over time. And this was 1978, which is before we have a lot more stuff up there now. Now we've actually had a collision already. I believe was it a Russian satellite collided with something. So we have a lot of satellites up there that we aren't keeping track of anymore. They run to the end of their lives. Maybe we don't dispose of them in the Pacific Ocean correctly, or parts of them break up. for one reason or another, we don't track everything perfectly. And the United States is not the only country putting stuff up there. And different countries have different ethoses about tracking stuff and even telling other countries that they've put stuff up. The United States certainly doesn't tell the Chinese about every spy satellite they put up, and vice versa. So there's a lot of stuff up there. And while there's a lot of space in space, which seems like a bit of a tautology, things are moving at, I forget the speed of low Earth orbit, but it's like in excess of 20,000 kilometers or 20,000 meters per second. Does that sound right, Frank?
Yeah, that's about right. Order of magnitude.
Okay, order of magnitude. So I'm within a factor of 10 is what that means. So things move very fast up there. And you run into things. That increases the cross-section for collision. So even though things are small, the satellites are small and space is big, the fact that they're moving so fast means that they've increased the amount of coverage that they have, which dramatically increases the chances of them hitting another satellite. And that, in turn, means that the collision itself is also going to have much more fun, because you can really do a lot of damage when you run into something at that speed, especially if it's moving at the same speed going in the opposite direction. And so the models that the United States government made, at the time and in the years since, are like, wow, we really could have a major problem. So the movie is based on a real premise. And then the debris cloud keeps coming around every 90 minutes. So there'll be like a period of quiet where Sandra Bullock and George Clooney can try to get themselves out of space. And then the debris cloud comes around again and all hell breaks loose. All of that is completely accurate. But we're going to end the screen share. How do I do that? Haha. All of that is completely accurate. But oh, Frank, you are muted? Okay, because I'm not big on the screen. I'm little on the screen.
I'm here.
It doesn't matter. I'll just use the little screen. I'll limit my screen sharing. So the total amount of time they have in between these collisions is correct. But the total amount of time that elapses between the initial collision and everything just going to hell at the beginning of the movie, that's not accurate. There's actually, the chain reaction would take at least a few days to get going. In the actual movie, it happens very quickly, a matter of minutes. And that's not actually what would happen in real life. So that's one little minor detail. Then there's a bunch of other things going on. They basically do a tour of everything major in low Earth orbit for the rest of the movie, trying to find a way to get back to Earth now that the space shuttle has essentially been destroyed and the Hubble Space Telescope has been destroyed. So first they visit, I think, the International Space Station, and then they visit the Chinese equivalent. And while it's true that all of these things are in low Earth orbit, Sandra Bullock and George Clooney kind of take this sort of leisurely tour of all the sites in low Earth orbit. Low Earth orbit is the size of the Earth itself, plus 90 miles or so, a few hundred miles. And it's a big place, and things are moving very fast. And as I said before, they're not all moving in the same direction. So if you can imagine trying to jump from a moving train onto a moving train moving in the opposite direction, it's not going to work out very well for you. Sandra Bullock and George Clooney do that throughout the movie, going from the space shuttle to the International Space Station. Those two things, the Hubble Space Telescope and the International Space Station, their orbits are unlikely to be close enough to do that. And if they are, they're not going to be moving at anything like the same velocity. So it will be like jumping from a moving train onto a moving train in the other direction, except much, much faster. Very, very difficult to reconcile those velocities. You're most likely going to end up with either missing it completely or a Sandra Bullock and George Clooney smear on the International Space Station. So that's not realistic. And then the thing that really drives me nuts about Gravity, and here's where the spoilers come in. Okay, so here's the spoiler. if you want to just mute or not listen to me for like the next 3 minutes, and I'll do a little wave at the end when it's safe to listen again. So if you haven't seen Gravity and you don't want this ruined, the wave means that it's safe, okay? All right, here we go. So George Clooney dies in the movie. That's the spoiler. And he dies because physics stopped working. So at one point, he and Sandra are trying to go from, I think it was the International Space Station to the Chinese space station. And they got tangled in a bunch of cords. And they couldn't stop themselves. They had too much momentum. And they hit the end of the cords. And at that point, the third law of physics, everything that has every action has an equal and opposite reaction, should bounce them back, and it doesn't. George, it's like a constant force keeps pulling them at the end of this cord. And George Clooney says, I'm going to release my tether and so you can save yourself. And so he does, and he cuts the tether, and Sandra Bullock is left alone in space without George Clooney, who's drifted off to a certain doom. Very tragic, heroic death that totally does not meet any of the laws of physics. It drives me, there's an invisible force pulling George Clooney into space, and I have no idea what it is. Drives me nutso. Okay, so all done. Spoilers are done. Okay, so that's Gravity. Good premise. And the execution as for scientific accuracy. But a very solid, very exciting movie if you're willing to suspend the laws of physics during your watching of it. Next movie, let's go to Interstellar. Interstellar actually pleasantly surprised me. There are considerable arguments online, and I'm happy to link to those in the discussion board if people are interested, between Phil Plait from the website Bad Astronomy and Kip Thorne, the Caltech general relativistic black hole wizard man, who actually first came up with the idea for the movie Interstellar and also acted as science consultant on the making of the movie. And with Phil Plait arguing that the physics is bad and Kip Thorne saying it's good. Now, they never actually directly interact. It's like, I feel like the middleman when I read their arguments, because they never actually directly address one another. Like, they make a list of all the things that are great about the movie, they make a list of all the things that are bad about the movie, and never the two shall meet. So I can provide links, and I can try to provide some translation between the two of them. But basically, Interstellar, I was really quite pleasantly surprised by, because all of that crazy physics that happens in Interstellar is 100% like correct. Time dilation really has that effect. Black holes really kind of do that. Black holes really kind of look like that. I'm going to do another screen share. At one point, they get very close to a black hole. They visit a planet that they describe as circling the rim of the black hole. It's not inside the event horizon, because it couldn't be. You couldn't visit a planet that's inside the event horizon of a black hole. But it's circling the rim like a basketball that wants to fall in, they describe it as. And there are problems with that planet. But you get a view of the black hole from up close. And it looks like this. Let's see if we can do the screen share. It looks kind of like this. View image. And this is what we really think a black hole would look like to someone standing outside of it. So the first thing you'll notice is it's not black. There's a dark interior, but there's an awful lot of very bright light around it. And that's the accretion disk. So when stuff falls into a black hole, and black holes do occasionally have stuff fall into them. Black holes don't suck like vacuums. Everyone says, oh, there's a giant black hole at the center of the Milky Way galaxy. Aren't we going to get sucked into it? No, we're not going to get sucked into the black hole. You have to be on an orbit that takes you inside the event horizon to fall into a black hole. Or on an orbit that takes you close to the accretion disk, where tidal forces can pull you apart. Because what's actually happening here is probably stars got too close to the black hole, and the tidal forces pulled them apart. And then they got shock heated to an extreme temperature of millions of degrees. And so this is the accretion disk around the black hole, which is probably comprised of stars that have fallen in. And I'm going to use the word fallen, not sucked in. And it's quite hot. So that part of the movie's 100% right. And the screen share. As is the notion that if you were on a planet that was very close to the black hole, or you were very close to the black hole, time would be different for you than it would be for people well outside of the gravitational influence of the black hole. And the way those effects works are in the sense of time goes by, a couple of minutes translates to years. A couple of minutes on the surface of that planet translates to years for people who are very far away from that black hole. That part is correct. The time dilation effects are correct. What's not correct, you wouldn't have a planet that close to the event horizon of a black hole, because the planet would also get pulled apart. Phil Plait points out that humans can't exist that close to the event horizon of a black hole, because they'll get pulled apart. It's called spaghettification. You get pulled into spaghetti strands as you get sucked into the black hole. You personally, as a human, your toes get pulled apart from your head, because the force of the black hole is so much stronger on your toes than it is on your head, so you get pulled apart. That's true for stellar mass black holes, but the black hole that they have in the movie Interstellar is called Gargantua. It's a supermassive black hole like we have at the center of the Milky Way. And for supermassive black holes, the tidal forces are tolerable for humans. So a human, at the end of the movie, a human falls into the black hole. And he doesn't get pulled apart like a piece of spaghetti. And that part is 100% okay, because it's a supermassive black hole, and the tidal forces are actually less for a supermassive black hole, even though the overall gravitational force is greater. And then there's a bunch of metaphysical stuff that happens with, like, love ties everyone together. And everyone complains about love tying everyone together. Love is not a force of physics. But we don't actually know what happens inside a black hole. Neither do you. Frank doesn't know. Frank's making a face like he thinks he knows, but he doesn't know. He doesn't know. Nobody knows, because general relativity breaks at that point. Quantum physics breaks at that point. So you're welcome to do whatever you like from a movie standpoint once you're inside the black hole, including time travel, which they do time travel by going into the black hole. And that actually, there's good reasons to think that that's a legit interpretation for going inside the event horizon of a black hole. Sure, why not? Other things that are not quite right. Back to the accretion disk around the black hole. When I showed you the picture of the bright disk around the black hole, the planet could not be that close to the black hole, and has like the black hole shines like a sun. So black holes that have accretion disks do shine, true. However, they do not shine like a sun. They shine in the X-ray and the gamma ray, which is typically not healthy for life on planets. So that actually is not a healthy environment for life. You would never go to that planet looking for humanity's second home. That's not a good planet to be, not a good place to be. So Interstellar has some flaws as well, but actually overall, I thought that it felt like a really great movie to me. It just held together. The relativity held together. The physics held together. There were some flaws in it from a physics standpoint as well. There was some suspension of disbelief, but honestly, I was really just delighted by it. And then the last movie is The Martian. And I'm going to say that if you're trying to decide between reading the book or watching the movie, go with the book. The book is so much better. The book is funnier. It's a little bit dirtier. But the Martian holds together because Mark Watney, the astronaut who gets stranded on Mars, is hilarious. And he's funny. He has a real gallows sense of humor about his, like, I'm probably going to die on this planet. And he's just very, he curses at NASA on a regular basis. And it's, and you don't get as much of that fun from the movie. They also had to shortcut a lot of really cool space exploration, neat facts in order to do this, fit it into a half hour or fit it into a 90-minute movie. And so you lose some of Mark Watney's awesome personality. You lose a lot of the really cool fixes that that either NASA comes up with or he comes up with on the surface of the planet to get himself out of this situation. But overall, it's like watching Apollo 13, which is based on a real thing, if you had to make up an Apollo 13 incident on Mars. And it's what it's trying to do. It does it, I think, very successfully. It's very enjoyable. But it is much more enjoyable in book form than movie form. I watch the movie after you've read the book. The two major flaws with it, okay, there's one major flaw and one so-so flaw. The major flaw of it is the event that puts Mark Watney into danger in the first place, which is a reoccurring dangerous threat on the surface of Mars, is the dust storms. The dust storms are why he's in trouble, because the dust storms threaten to knock over their ascent vehicle to get off the planet, so they abort the mission. The dust storms blow the antenna off of they have a little base on the surface of the planet they call the HAB, where it's an Earth atmosphere inside. And the antenna gets broken off during the dust storm, hits Mark Watney and blows him away, and pierces his suit, actually. So he's exposed to the Martian atmosphere briefly, and everyone thinks he's dead. And Martian winds are never going to be strong enough to knock things over. Martian winds are never going to be strong enough to break things off of Earth-based equipment. That's not something Martian winds can do, because the atmosphere on Mars is something like 100th as dense as the one on Earth. Is that about right, Frank? 100th? 1000th? Where are we at? I get like the order of magnitude between Venus and Mars confused. One's 100 times thicker, one's 100 times less thick, but it might be 1,000th. The atmosphere is so thin on Mars that even when the dust gets blown, you never pick up big enough particles. There's not enough force behind the wind to do any real damage to anything. What the winds do, and what the dust storms do, and which they do actually later in the book, he comes with a really plausible scenario for ways in which dust storms can threaten astronauts. The dust storm becomes so thick that it blocks Watney's solar panels, like the light coming down. The solar panels can't get enough light to produce enough energy to even run his life support system. And it actually, threatens to kill him, basically. That's a 100% realistic scenario, because that's actually how we've lost Mars rovers, or just dust storms come in, they lose the ability to charge with the solar panels, and the solar panels themselves become coated in dust, and that's it for a rover. So that's right. The movie doesn't make any mention of something called perchlorates. I'm going to do another brief little screen share so you can look this up. And I actually had a conversation with none other than science fiction writer Kim Stanley Robinson. Kim Stanley Robinson was the first person to mention perchlorates to me. So perchlorates are a kind of chemical that is found in the Martian soil. And it's been found at every rover and lander site that we've had the technology to look for it. And at something like 0.5% level in the soil, it's very, very common in the minerals, and it's very, very toxic to humans. And so there's a lot of reasons why going to Mars is still considered a one-way ticket for any astronaut who chooses to undertake such a mission. Perchlorates are just one more reason why that's probably true. In addition to the radiation, the expense of getting someone back. Perchlorates, we're going to have to think, if we really want to go to Mars with a manned mission, we're going to have to think very hard about how to limit exposure to Martian dust, which Mars is a dusty environment. It's really hard to avoid dust getting in the cracks in your spacesuit, finding its way into your stuff. It found its way into all sorts of things when people were doing moon missions. The moon dust and Mars dust is just going to be everywhere, and it's toxic. So how to deal with that is something that the book didn't even address. So I think those are two things for the Martian, and there's just a bunch of emergencies that get added for dramatic tension, but it's still a very enjoyable thing. And I think I'm done with those two. And you can ask me more questions in the discussion forum if you want more clarification. or links. I'm all done, Frank. You're on.
Cool. That was nice. So no Martian potatoes.
Yeah. Well, I'm not sure. The potatoes seemed not unreasonable.
No, with regard to the perchlorate.
Yeah, well, I mean, you can have the potatoes. I'm just, not convinced they wouldn't kill you in short order. But
kind of like stuff in your water or something.
yeah.
And yeah, I did do a quick lookup, and you were right. The Martian pressure is somewhere between 100th and 1,000th. That's exactly right. Okay, what I'm going to do is pick up on Jackie's theme there of rocket ships, and we're going to do a little rocket ship action to the sun. Since the sun is one of the bodies that we haven't really covered in this course. And I'm going to do a screen share, and I want to share. Do you still have your screen share on?
I shouldn't. Let me just double sure. No, it looks like it's off.
Okay, screen share. Okay, got it.
You got it?
Okay, start screen share. It's on now. I'm gonna go over here, and let me know if you can see this.
I can see it.
Okay, should be full screen. Okay, so we'll do a little 20-odd slides here on the sun. So all cannot live on the piazza, meaning the plaza or the central square, but everyone may enjoy the sun. Italian proverb. So we're going to take a little journey to the center of the sun, and if you think the ship that we will need to go to Mars, as Jackie described, will have to be robust. It's going to have to be a little even more robust to get to the center of the sun. And I just kind of like this piece of artwork on a spaceship. So as we begin the journey from the sun is going to start off looking like a ball of glowing gas. It's got some dots on it, which of course Galileo was the first person to take a look at those zits on the surface of the sun. And the total power output of the sun is a whopping 3 times 10 to the 26 watts, 4 times 10 to the 26 watts. And if somehow humanity could capture about 1 second of the sun's luminosity coming out, it would meet all of our current energy needs for about the next 500,000 years or so. So there's a tremendous amount of energy coming out of the sun relative to human needs. And of course, there's this whole, I forget exactly what they're called right now, but there were sort of these type 1, type 2, type 3 civilizations that depended on effectively how much energy you caught from your parent sun, which I remember the type 3 civilization being one that is able to harvest all the energy coming out of its local thermonuclear reactor sun there. We're not at that level yet. In fact, the Earth only intercepts, and all we ever do is take a very small, tiny portion of that tiny fraction that comes from the sun's total energy output, with the rest of that dispersing in all directions into space. And I think you even have a lab question this week asking that question: what is that fraction that the Earth receives from the sun? So this image here is actually a split image between in 2 filters, one in H alpha, which is on the left, and then one in a white light filter, which is on the right. And so you're actually looking at 2 different layers of the sun when you take a look at this. There are different depths, there are different heights in the sun. And we're going to take a look at some of those heights. So it's true that most of the energy is radiated from the sun in the form of visible light. That's why we see invisible light. Our eyes are energy-seeking devices. And so they gravitated to where most of the energy was, which is in the form of visible light. But once we sort of leave that protective blanket of Earth's atmosphere, we're going to encounter other types of solar radiation, everything, especially in the high energy range, from the ultraviolet to the X-rays. And I love this image shown below. This is a shot from the New Star satellite, which is a current NASA mission up and going. And it is an X-ray satellite. And so it looks both at the sun, it looks at the solar system, and it looks at the galaxy and extragalactic stuff for what that material is radiating in X-rays. And this is a very colorful, active shot of the sun in X-rays with the different colors representing different energies, different wavelengths of the light that is coming out. So we're going to need a lot of shielding as we go into the center of the sun from these high energy forms of radiation. And I just kind of like this art piece from Bill Arnett showing a couple of past centuries, the current, and perhaps the future of what spaceships travel devices look like. We start off with traveling across the oceans in our Clipper ships there. We have the current space shuttle type of technology. And then of course our art, our science fiction points us to what some of those designs might look like to travel amongst the stars and perhaps to the black holes of interstellar that Jackie mentioned. So with spectroscopy, as we start our journey to the sun, we can verify that the sun is basically made out of hydrogen, 70% hydrogen, 28% helium. And in fact, it was from the sun that helium was even discovered as an element. It doesn't exist in a significant abundance here on Earth. And so the identification of the second most abundant element in the cosmos came through looking at spectroscopy of the sun. And the sun is currently about 28% helium. And all the other stuff, the carbon, the oxygen, the iron, all the stuff we're made out of, is the heavier elements. You've seen this image down below before when we were in week 3 with light. And so you know all about rainbows with holes and why those holes are there. And each of those holes coming from an atomic transition from some element, whether it be hydrogen, helium, or any of the other 2% of the heavy stuff. So when we look through a telescope, we can see that the sun is seething with churning gases, and at least a few sunspots sort of blotch the surface, and they move across that surface. So the image here shows from about 2001, this is from the SOHO satellite, a group of sunspots, a relatively large set of sunspots, moving across the face of the sun. Down there on the bottom part of that image is a dot representing the size of the Earth relative to those sunspots. You can see the sunspots are huge. Sunspots are actually not dark. They're blindingly bright, but they only appear dark relative to the even brighter solar surface that surrounds them. So they're little cool areas on the sun, and they move across the face of the sun. Why do they move across the face of the sun? Because the sun is rotating. Okay? And it rotates at different speeds at different latitudes. So near the equator, the sun spins. It takes about 25 days if you had a marker such as a sunspot to go around and come back. Whereas by the time you move up to the poles, it's faster. It takes about 35 days for a complete circle to be made. So the sun is not a solid body rotator. It's a ball of gas. And so different latitudes can and do rotate at different rates as you go through. So as we continue toward the sun, we're going to notice an increasingly powerful headwind that's going to put a drag on our spaceship. And this solar wind is created by photons, the radiation, but also particles. There are protons, there are some of the helium nuclei, there's even heavy elements. So basically everything that the sun is made out of can come, and what it's generating and emitting, along with electrons, stripped electrons from those atoms, come flowing out from the solar surface. This is an example of a cutaway. This is some of the regions we're going to be going through here soon. We're out here in the solar wind area. Soon we're going to go into the corona, and we will transition to the chromosphere, into the photosphere, down into the convection zone, the radiation zone, and finally into the very center or core of the sun as it goes. So the solar wind helps shape the magnetosphere of planets. It can blow off the material that forms the tails of comets or planets that don't have a sufficient magnetic field. So the image here is Mars on the left and Earth on the right. Earth, of course, still has a very active dynamo in its center. It's still warm in the center, and so that fluid moves around, and that creates a magnetic field, which, thankfully for us, gives us protection from the solar wind. Mars probably had it at one point, but Mars is small, and so Mars is geologically dying, and once it did that, it lost its magnetic field, and so then once that solar wind can get in there, it will strip your atmosphere fairly quickly, leading to residual atmospheres, as Jackie mentioned, that have about pressures of about 100th to 1,000th of what they were perhaps originally.
To be fair, Mars's atmosphere probably also froze off.
True. Also oxidized.
Yeah.
Thermal escape, all of it. It had a whole bunch of bad stuff happen to it as far as life goes. So now on our journey to the center, we're about 1 million kilometers or so from the solar surface, and we enter the realm of the corona. And this is the uppermost layer of the sun's atmosphere. It's kind of equivalent to the exosphere of Earth's atmosphere. And you can really get a really nice images of the solar corona during solar eclipses, and that's what this image shows. That big dark spot in the middle, if you look a little closely at it, is actually the moon in front of the sun. And then you have all these streamers and curved features of material streaming out from the sun in that hot area known as the corona. So you can actually image the corona during solar eclipses, or with the right equipment, you can block out the disk from the sun and take a shot of the corona at will. The temperature in the corona is hot. It's about 1 million degrees Kelvin, which is almost as hot as the center of the sun. So the very hottest parts of the sun are the core and just on the outside of the sun. But you don't feel that heat too much because the density is so low out there. So the temperature is a measure of how quickly the particles are moving, but you don't feel it so much in your spaceship because the density is still very, very low out there. And it is this low density, high temperature material in this layer of the sun that emits most of the sun's X-rays. So this image on the right is also from the SOHO satellite. And again, it is color coded by temperature. So red is about 2 million Kelvin, green here is about 1.5 million Kelvin, and blue is about 10 to the 6, 1 million Kelvin as you go through. And you can see that there are different temperatures swirling around inside that corona as it responds to basically sort of weather in the corona with different features going on. You've got prominences, you've got flares, you've got spicules, you've got all kinds of phenomena going on there. And you see that reflected in sort of this swirling color collage-like item when you look at the sun in the X-ray band out in the corona. Continuing further in, the temperature suddenly drops from a few million degrees out in the corona. It drops relatively abruptly in what's called the transition zone into the chromosphere, which is where most of the ultraviolet is going to be radiated. And then finally, the sun has a little temperature minimum as you get into what is called the photosphere. And the photosphere is where the visible light, most of the visible light is emitted from. So you've got the corona X-rays, the chromosphere ultraviolet, and the photosphere in the visible light. And so this plot here is temperature is a function of height, and you can see that very quick transition as you go from the corona to the chromosphere in that transition zone. So as mentioned, the chromosphere is the primary source of the sun's ultraviolet light, and I just sort of love this image here. It reminds me of a flower almost. This one is taken from the NJIT solar telescope, and it's actually focusing in on a region around a sunspot. And the structure that you're seeing here is primarily due to the magnetic fields of the sun, sculpting the gas, sculpting the material that is emitting the ultraviolet radiation. So a little bit of a pink flower art in the chromosphere of the sun. The chromosphere is also a location where there's a lot of weather, so to speak. There's a lot of flares, prominences. This is another example coming from the SOHO satellite. of the limb of the sun. And the colors here again represent different temperatures, different wavelengths of light, this time in the ultraviolet. You can kind of see the locations there of sunspots. That's where there's sort of a convergence points of color. And that's really a convergence point of the magnetic field. You can see some loops on the outside on the limb of the sun there, on various flares and prominences as they sweep out from those magnetic fields. And I think it's just a very pretty picture of the sun. It's almost impressionistic, if you like. And at last, we plunge through the visible light surface of the sun, the photosphere, where the temperature is about 6,000 K. So when people ask, what is the temperature of the sun? What they typically mean by that is, what is the temperature of that visible light surface, which is about 6,000 K, considerably cooler than what it is out in the corona or even the chromosphere. It's around sort of the temperature minimum of the sun, actually, is where that visible light surface is. And as we go through that solar atmosphere, we've noticed that the sun has had a lot of weather with magnetic fields, flares, and a lot of turbulence. It's that turbulence, that convection, that is driving it's the boiling liquid of the sun, if you like, the boiling gas. And so our compass on our spaceship is going absolutely nuts. And it's going nuts because the material is convective. It's moving around. Hot material is welling up. Cooler material is sliding down. And there's no set direction to that magnetic field. So we're getting tossed around, and our compass is becoming effectively useless as we go through the solar atmosphere. So as we go now beneath the photosphere, the blazing light that surrounds our ship is getting tossed around by this turbulence. We can see, as I mentioned, hot gas going up, cooler gas going down, and we are in the convection zone of the sun. And this is where energy is transported by convection, by the bulk motion of material as it attempts to cool off. It's hot down below, and so it's trying to transport that energy out. It can't do it smoothly by radiation or by conduction, and so the only thing that's left is to make the material move, to make the material boil in a turbulent convective environment. Again, there's our layers. So just for orientation, as we head down our journey, we're now into the convection zone. And what you see is in this convection zone that the photosphere, where the visible light is at the top of the convection zone. And so it's that visible surface. This is what gives that the sun that churning appearance. So here in this image here from the Vacuum Tower telescope, this is focused around a sunspot. But around that sunspot, you can see what are called granules in the photosphere, where you've got bright areas, white areas. This is hot material that is welling up. Surrounding each of the granules is a darker region, and that darker region is cooler material that is then falling back down more toward the center of the sun to pick up more heat, get heated, and rise back up again. And so you get this sort of this boiling pot look to the very top of the convection zone, which is also where the photosphere is. About a third of the way to the center of the sun, that turbulent boiling region gives way to a much smoother, what's called the radiation zone. And instead of being transported by the bulk motion of material here, energy can be transported strictly outward by photons. So it's a very quiescent ride for our super spaceship that is making it into the center of the sun. Again, this is another shot from NASA showing the various structures of the sun. We've just left the convection zone and we are headed into the radiation zone. And finally, we plunge down to the core of the sun. And at the center of the sun, the temperature is about 15 million K. So on the order of about maybe 10 times hotter than what it was at the corona. The density is about 100 times that of water, so it's about 100 grams per cubic centimeter. And you're at the very heart of the energy producing region in the sun. This is where protons get together with other protons. It is hot enough, they have enough speed where they can bang into one another, overcome their natural repulsion, right? They're both protons, so they have positive charges and they want to repel each other. They don't want to get together. But if you've got enough energy, you can make them overcome that electrostatic repulsion. And when they get together, they will then fuse to form helium. And in the process, E equals mc squared operates, and you get energy gamma rays coming out of that process. So I kind of just love this image because it's actually a modern encyclopedia. It's a digital modern encyclopedia. I'm sure there's an ad here somewhere. Yes, there it is down at the bottom. Dorling Kinserly. I want to check it out. They do some very interesting encyclopedia work across a wide variety of topics. And they have fantastic graphic images on the stuff that they cover. So the encyclopedia is not dead. Wikipedia is not the end all be all. You can still have some very visual orientated encyclopedia material. So how do we know this stuff? Yeah, we just told a picture. How do we know any of this stuff? So one of the ways that we learn about the inside of the sun and other stars actually these days is to observe sunquakes. These are vibrations of the sun caused by the pressure waves, sound waves that are bouncing around the sun all the time. And the image there is from that other encyclopedia, Wikipedia, showing some of the different types of bouncing around of different sound waves that you see. The dominant mode of sound waves of breathing in the sun is about 5 minutes. So the sun sort of pulses on about 5-minute time scales at its most common frequency. There's a whole bunch of different oscillations going on, but the 5-minute one is about the dominant one. And although you can't obviously go to the sun, although we have our super spaceship, and set up a super seismometer on the surface of the sun, what you do is you can detect vibrations of the surface by using light. There will be subtle differences in the brightness of the light depending on whether material is coming out or going in, so kind of a Doppler effect scenario going on there. And so by analogy with what we call seismology on Earth, this type of telescope, it allows us to peer inside the sun deeper than the photosphere, is called helioseismology. And it's from helioseismology that we can probe the structure of the outer layers, both the radiation zone, where stuff is relatively smooth, and then the turbulent convection zone, layers we would have no idea what was going on with otherwise. And this is a relatively new topic in astronomy. It's probably no more, well, for the sun, it's a little older. For the sun, maybe 20, 25 years, maybe 30 years. For other stars, things like the Kepler telescope, which is an example of which is shown there on the right image. That's much newer, certainly less than 10 years. And what these images are showing, where you see sort of this patterned region, this is where the waves, the sound waves, as they bounce around, sometimes just like light, they will sometimes interfere with each other constructively. And so you'll sort of, in some sense, double the amplitude. And in other cases, those waves will cancel. And so you will basically get a quiet zone, and you get this pattern of oscillations set up within they're like standing waves. They're standing waves set up inside the sun and other stars. And from that, you can learn a whole lot more about the outer regions, particularly the convection zones and the radiation zones. But how do we know anything about the core? Well, another way to study the solar interior, in particular the very center regions of the star, is to take a look at some of the particles that flow out from those fusion reactions that go on in the sun's core. And in particular, neutrinos are a nice diagnostic of the interior of the sun, if you can catch them. So right as I'm speaking this sentence, roughly on the order of about 10 to the 18th solar neutrinos are going to go zipping through your body right as I'm saying this. Fortunately, for life anyway, they don't do any damage. Neutrinos rarely react with anything. It typically takes on the order of a light year of lead to stop a neutrino. That's a lot of lead. So while they hardly interact at all, that's not to say that they do not interact at all. On occasion they will. And so if you have enough material and you monitor things carefully, you can catch a precious few of those neutrinos. And the energy of those neutrinos are telling you about the conditions in the center of the sun. And that's what we do with two telescopes of these sites. These are like neutrino telescopes. One of them is called Borexino. And I love this sort of like spacey looking shot. Looks like something out of one of the movies Jackie mentioned there, of this bubble region. All those tubes around it are basically looking for a particular type of light that comes out from the Borexino.
That looks like a Martian potato farm.
Yeah, doesn't it? Yeah, that with the translucent dome there, right? It looks kind of alienish almost. And so this is the type of telescope that you use to study what's going on in the center of the core. This is one. Another one is this lovely array of light tubes. And if you look carefully, those guys in the middle, they're actually, yes, they are floating in a boat. This thing is filled with an ultra pure water, and you are looking for a particular type of light coming out. When one of those rare neutrinos happens to interact with your water, it will produce a particular type of light, Turkanoff radiation, sonic boom in water, if you like. So you're looking for the sonic booms in water as they go through. And it's the capture of these types of neutrinos that proves that the sun runs on thermonuclear power. It's not contraction. It's not a giant fire in the middle with coal or wood. It is nuclear powered, and we have direct experimental proof of that. And because of the energy that comes out, not only do we have proof that it does happen, but we know definitely what the conditions are at the center of the sun. So about 15 million Kelvin, densities of about 100 grams per cubic centimeter. So in the core, so once you get one of these reactions to go on that releases one of those neutrinos, these are high energy fusion reactions, and they release a gamma ray, a high energy photon that typically only travels about a millimeter, a fraction of a millimeter, before it starts colliding with something else. Okay, and so each collision sends this high energy gamma ray photon off in a random direction, and the photon sort of bounces around in sort of this haphazard, random way. But eventually, the photon does make it out. It does sort of what's called a random walk. It does a diffusion type of process to get out. And with each of those collisions, the gamma ray photon eventually loses some of its energy with each collision. And so taken it at whole value, once you produce a photon in the center of the sun, it takes about 1 million years for that photon to reach the center, and where that one gamma ray photon has now been converted into about 1,600 visible light photons when it leaves the visible surface. So there's just a couple of numbers there to remember. It takes a photon about 1 million years to get out from the center of the sun, where neutrinos just go streaming out. They're not bothered by anything at all because they don't interact. So they just go booming right out of the core. And each of those gamma ray photons gets down-sampled, down-converted to about 1,600 photons on its way out. And some of those 1,600 photons manage to make its way to illuminate the surface of the Earth, where if you happen to have some a space station, International Space Station, which is not too densely populated with other stuff, so that we run into one of the movie scenarios that Jackie mentioned in Gravity, you can take a very lovely picture of our little spot in the universe. And that'll do. Thanks. Okay. And
you want to talk a bit about the necessity or lack of necessity of manned spaceflight missions or exploring Mars briefly? So two people asked about manned spaceflight. There was a question about manned missions to Mars, and then there was a question about, like, is it inevitable that we must go to Mars? And then there was another question about manned spaceflight in general, whether or not.
yeah, a lot of it was manned spaceflight questions.
And the thing about, we can discuss that. We can even argue, pick a side and argue it, but we can't answer those questions because they don't have answers.
They have informed opinions, but it's an open area of debate, and so I mean, Frank, would you like to argue for manned spaceflight or against it?
I can take either position, but I will argue for it, or
Okay.
I'll present some of the arguments that people give why manned spacecraft. Hey, we got a question there. Why manned missions are still something to do.
Where do we have a question? We have a question.
One came over the Q&A there, I see. So one of the arguments given is that humans are still, okay, so first of all, just from an economic standpoint, robots are going to win. They will end up doing the bulk of laissez-faire type of data collecting, but humans are still superior when it comes to exploration. Humans can take in all kinds of information coming in and very quickly pick out what is unusual, what is different. That's an unusual looking rock, or what's that thing over there? So humans still have a much finer sense of what exploration means, as opposed to going there, okay, I'm gonna measure some neutrons, I'm gonna measure some photons, let's just march over here and measure some stuff. Robots are not aware of everything that's going around them and can assimilate it and do that exploration.
But the robots don't actually assimilate. Wait, hang on.
I can't really hear you there.
There we go. The robots don't actually do that assimilation or decision making. I mean, what happens is during Martian night, all that information gets sent back to Earth, and then a course is plotted based on the information from the robot. So actually humans are interfering and intervening with the robot, and it's really sort of a question of how many tools you equip the robot with and whether or not you're willing to accept the light travel time.
Correct.
There's commands going back and forth.
Correct. But in the moment, I'm there, what's going on? The human excels at that kind of exploration.
So the number I've heard for manned spaceflight versus robotic spaceflight is a factor of 100 in extent.
Oh, I'll believe that.
Easily. Because you have to, with a robotic mission, you have to have technology to go to Mars, for example, is really, as opposed to just creating the same thing on Earth, is again 100, 1,000 times more expensive, because it has to be spaceflight tested. And spaceflight tested doesn't just mean that it has to endure the rigors of space. I mean, someone has to actually be paid. Most of the money that goes into making spaceflight happen is in people's salaries.
Right.
And those are the people who make sure that
ever fly.
Yeah, they're the people who make sure that these things actually do get tested before they fly and to Mars. So there's this huge overhead that goes with making sure something's spaceflight tested before you send it to Mars. But essentially, with going to Mars with a robot, you need to just not blow up. And partial failure is kind of
the loss of a robot is okay. The loss of a human life
is less okay. Because and the funny thing is, astronauts really are in The Martian. They talk about this. They talk about will Mark Watney's 5 companions, are they willing to add 500 extra days to their mission, and a lot of risk to themselves personally, to fly back to Mars to try to pull him off the surface or intercept him, as the case may be. But and down at NASA, they're like, we're going to make this decision without them because we already know they'll go for it. And they do this constant thing that's happening at NASA where they're trying to make decisions for the astronauts, because they know as soon as they give the astronauts the choice, they will do the selfless, crazy, heroic thing every time. And that's true. There's some fraction of humanity that is totally willing to take the one-way ticket to Mars every time to have the chance to go to Mars. And I'm reluctant to say that we have the right to take that right away from them. That said, when you're doing the calculus from Congress's point of view, so the United States Congress has to fund it. Congress, every time we blow up a human being, Congress wants to cancel all of NASA, like every time. There's a huge inquiry, and all of spaceflight is endangered because a human accidentally got blown up. So regardless of what the astronauts think about astronauts' lives, Congress will totally end all of spaceflight. So manned missions are 100 times more expensive just because you have to make everything function all the time so that you can get your humans back to Earth safely. But they're also expensive. There's a lot of risk because if you lose a human astronaut, then Congress is going to cut you off. So
why do we do it? So why do we do it, right? So it is something that our art, whether that's in drawings or movie pictures or books, all of it is pointing us toward leaving Earth. Traveling amongst the planets, traveling amongst the stars, it's a destiny that is, I think, in some sense, deeply implanted in our collective psyche. And current situations of Congress or no Congress, in the end, I think that's what we will do. We will learn to overcome the hazards, the dangers, and we'll do it.
I mean, there is the argument of like you can't.
There's a romantic notion to it, right?
Well, beyond the romantic notion, which is tied in with a very colonial idea. So this is a global class. It's not just an American class. And in America, we have this concept of manifest destiny. Humans are supposed to explore all of space because that's what humans do, and they're supposed to conquer all of space. And the idea of conquering America is taught to us from the beginning when we're first graders or kindergartners, and we learn about Thanksgiving and marching from the Atlantic to the Pacific. Well, there were people there. And it's not necessarily the case that there are people on all these other planets, but we have this in our head that we're supposed to conquer things. And that's a very colonialist idea, which is not always cool if you're looking at the perspective of one of the people who was conquered recently in human history. So the idea of a post-colonial spaceflight program is going to be an interesting discussion that we have. There's also the question of like, we motivate spaceflight because of the meteor impact danger. We motivate spaceflight because eventually we will run out of sun, although that's way down the line. But the meteorite, the asteroid impact thing is a real thing. But shouldn't we fix global warming first? Shouldn't we invest the resources into fixing climate change? Or as my friend and yours, sarcastic Mars rover put it, my very, very favorite Twitter user, sarcastic Mars rover, says, "Reminder, fleeing to Mars is not an option. You will die here. Stay put and fix your dumb planet. Do not come to Mars."
My only regret is that I won't come back, neither will you, in a million years and see where we are. And I'm the optimist, so I think we get there. We do have a question. There was one question. I guess it was brought up by your interstellar review. And I don't know if you can see it. I'll just read it. Why do supermassive black holes have weaker tidal forces than stellar black holes?
So yeah, I'm gonna have to actually like do the math on that one. But Frank, do you remember why it is? It's because the tidal force is the derivative of the gravitational field. So it basically is stating that the gravity is falling off less quickly as you move away from the black hole. So basically it says that with a stellar mass black hole, the gravity is falling off more quickly. So there's less, so if I'm standing on a stellar mass black hole, let's assume that that's even possible. On the event horizon of a stellar mass black hole, the amount of gravity that my head is feeling versus my toes is dramatic. So much so that it's actually enough of a difference in the gravitational pull from the black hole at that point that my feet will be ripped off of my head at that point. There's such a difference in the gravity falling off. Whereas that's not true. The gravity, I'm not, it's not that my head is experiencing less gravity or my feet is experiencing less gravity around the supermassive black hole. It's that my head is still feeling a lot of gravity. Both my head and feet are still both experiencing a really, really large amount of gravity, but the difference between that gravity falling off is slight. And I think that has to do with just the sheer size of the black hole, that its gravity field.
Why, you know?
Oh, there is.
I don't think there is a difference in the tidal force.
There is. I'll go find you a link.
Why would there be a difference in the tidal force?
Between a supermassive black hole and a stellar mass black hole? Between a 10 million solar mass black hole and a 1 stellar mass black hole?
Okay, so it depends what you mean by tides here, because the overall strength of the gravity is certainly stronger in the supermassive black hole.
Yeah, but there's a thing where, like, the tidal forces, a human being can survive in quotes.
Oh, well, that's a different question. All right.
Yeah, right. So, like,
Okay.
the tidal disruption from a human-sized body falling into a black hole, a supermassive black hole, is not sufficient to pull, for example, a human being apart, whereas it absolutely is sufficient falling into a stellar mass black hole, which in terms of the supermassive black hole should have more gravity. That sounds backwards, but it's actually the change in how the gravity is falling off with distance from the black hole that sets that. And at some level, this is about tides. This is about tides.
Yeah, it's a tidal effect.
Mass black hole tides. Okay. I'll Google it really quick.
My curiosity. I'm gonna work on this one. Okay, so we're a little after 11. We should probably call it quits on this number 2 here.
Yep.
So that was fun. That was good. I enjoyed your movie one. That was nice. I'm glad you finally saw those movies.
Yeah, fun fact, I actually watched, I had seen Gravity before I started teaching for this class. And Interstellar and The Martian were very specifically watched as a result of people wanting to hear about the bad physics. So hang on, before we end, Frank,
yeah.
I found a link. So I'm just going to screen share this really fast. Here we go. Here's a link on black holes and tidal forces. And I'll post it in the discussion boards, but it is about which black hole, there's problem 5, which black hole could a human enter without being, and here's a technical term, spaghettified. And down here at the bottom, supermassive black hole because the tidal force is far less than a human normally experiences on the surface of the Earth.
Okay, right. I think the whole thing hinges on what you're choosing for the distance.
I think it's, close to the event horizon. The event horizon is actually the distance in question. Okay. All right.
Good question. Good. Okay. We're good. Thanks. Thank you, everyone. I'll post the links on the discussion board so you can watch it on YouTube or watch the recording in reverse. And thank you. And this is week 7 of this course. And so you'll have your final next week. The final will be very similar to the other quizzes that you've taken, in particular quiz 2, the proctored quiz 2. So do well, do great. It's been fun. Thanks. Bye-bye.